Now here's an interesting idea. What if we had a parallel plate capacitor? So we have this right here, and it's got some area, and so we know the capacitance is epsilon naught A over D. Now, what would happen if we were to break the parallel plate capacitor here so that this is 2/3 A and this is 1/3 A? So we break it so that it's exactly the same here. So this is the same D. Okay, so we know that the total capacitance is going to be equal to C1 plus C2, because I already talked about how parallel capacitors work. And so what we've got here is we got epsilon naught 2/3 A over D and plus epsilon naught 1/3 A over D. So all that together is just epsilon naught A over D. So if you take a parallel plate capacitor and you just simply break it and separate the two parts, then basically it's the same. Okay, so in other words, what we're getting here is that for a parallel capacitor, you're basically just saying, hey, this is all one equipotential here, this is all one equipotential, so it's just as if you just stuck the two together. Okay, and that's why parallel capacitors add the way that they add. So let's do another interesting example here. Let's say that we've got a parallel plate capacitor here, okay, and let's say the plates here, have some area A, and there's some separation D right here. So the total capacitance is epsilon naught A over D. Okay. Now, what I'm going to do is I am going to slide a piece of metal in here. And let's say that the metal has some width L. And so that means we have D1 and D2 above and below. Okay, so in other words, the total D is D1 plus D2 plus L. And so I want to know what is this capacitance if I stick that in there. Okay, and so you look at it and say, well, gosh, okay, we know that if that's a piece of metal, it's an equipotential. So that means the upper surface of it acts like a plate of a capacitor. The bottom surface acts like a plate. And so this is going to look like two capacitors like that, okay, in which they still have the area A, and this is going to be D1 and D2 right there. Okay. And so the capacitance here of the top one is going to be call it C1, that's epsilon naught A over D. And for C2, that's going to be epsilon naught A over D, except this is D1 and D2. Okay. And so we know how capacitors in series add. So the capacitance is going to be 1 over C1 plus 1 over C2 to the minus 1. So in other words, that's going to be equal to D1 over epsilon naught A plus D2 over epsilon naught A to the minus 1. In other words, the capacitance is going to be epsilon naught A over D1 plus D2. Okay, now notice I had this capacitor here. The upper plate was area A, lower plate was area A, and I stuck a piece of metal in there that was length L, and what was left was D1 and D2. Okay, so the capacitance is just going to be epsilon naught A, D1 plus D2. It doesn't matter how big L is. What all that matters is the clear space in between. It also doesn't matter where L is. I can slide this metal piece up near the top. I can slide the metal piece down near the bottom. As long as the clear part is D1 plus D2, then that goes into that equation, and it doesn't really matter. So that's how you would solve that problem right there. So it's an interesting sort of thing that the only thing that matters is the clear space in there, not where that intercalating part would be. Well, now let's make it a little more complicated. So let's say that we've got our metal plates here, and I stick this metal piece in part way. So the metal piece comes in, and if that's A, let's say the metal piece covers half of the area. Okay, so let's say that half of the area is over here where there's nothing, and half of the area is over here where we have a D1 and D2. Okay, and that's D right there. Now remember what I had before. You know, another thing I could have done when I had before was epsilon naught A over D1 plus D2. That could have been written epsilon naught A over D minus L, because L was the part that was left in. D1 plus D2 is whatever was left over. Okay, so you look at it and say, now, how would we solve this problem up here? Well, this problem looks like two capacitors. One capacitor over here that's like half a plate, okay, and one capacitor over here that's half a plate with something in between and half a plate. So what's the capacitance on this side? That's epsilon 1/2 A over D. What's the capacitance on this half? It's epsilon A, 1/2 A rather, over D minus L. Right? Because I said that this is equal to that. Okay. Well, what happens if they happen to be in parallel? Well, total capacitance would be epsilon naught 1/2 A over D plus epsilon naught 1/2 A over D minus L. Okay, so this is going to be equal to epsilon naught A over 2 times 1 over D plus 1 over D minus L. Okay, really, I mean, it would probably be a good idea to find least common denominator, make this thing pretty, and so forth. So if you wanted to do that, that would be epsilon naught A times 2D minus L divided by 2 D times D minus L. Okay, so that's what that would look like if you put it all together in one fraction and made it look neat. Okay, so that's how you do it. These problems are not that tough with parallel plate capacitors compared to some of the other things that we've been doing.